Okay, welcome to part two of our lecture video series for Wednesday, April 12th, where we are going to review some more stoichiometric concepts, specifically looking at titration. So we have, at this point in this lecture, gone over already our first few titrations where we've standardized our sodium hydroxide solutions for KHP. And up next on Thursday, we are now going to do a titration in order to analyze how acidic vinegar is according to its acetic acid composition. So let's go over kind of the stoichiometry of what's happening in a titration. So in order to do that, we need to remind ourselves about what is happening in an acid-base titration. So reminder, when we are looking at an acid-base titration, we are looking at a neutralization reaction that is being controlled, right? We're having a controlled addition of what we call the titrant. Could be either acid or base. This is what's in the burette. To the analyte, which could also be an acid or base, depends on what we're looking at. And when we are adding acid to base or base to acid, we are always looking at a reaction where we have acidic protons reacting with hydroxide anions to create liquid water. And this is where the name neutralization comes from. We generate water as a product, meaning our pH of our solution ideally should be neutral or very, very close to, certainly neutral at the equivalence point. Where by definition, we have added equal number of moles of acid as we have base, hence equivalence point. And at the equivalence point, when we have exactly the same amount of acid particles, or H plus, that is equal to some amount of base particles, our hydroxide particles, then we see a perfect neutralization and we form H2O, and when we have no excess H plus or OH minus left over. So that is the equivalence point of a titration. Now, remember when we did our titrations for our standardization of sodium hydroxide, yes, we were controlling how much of our KHP we were adding by using a high precision volumetric device called our burette. So remember, a burette has the same uncertainty as like a volumetric flask or even a volumetric pipette, which is why I'm calling it a high precision instrument. And we were able to control that addition within pretty good precision using small drops so that we could get as close to the equivalence point as possible. However, this idea of perfect equivalence, like adding the exact same number of acid or base moles to your analyte, is not something that's really super realistic in a lab setting. So what we were witnessing in the lab yesterday is the endpoint of a titration. So in Chem 210, we're going to effectively call these the same, but in Chem 220, we are going to make a distinction between the two. So the endpoint of a titration, this is the point at which just enough titrant has been added to neutralize the analyte with a slight excess of titrant in the flask. So we've neutralized our analyte with a slight excess of titrant. So we haven't been able to add the exact number of acid or base particles needed to neutralize our acid or base analyte, but we have added just enough plus a little bit extra, which is why we call it our endpoint. And we witness this endpoint, so this is an eyeball looking at something, when we observe a color change as a result of an indicator, where an indicator itself is some acid or base, that is highly sensitive to the solution conditions, or pH, that it is present in. So in our titrations yesterday, we were looking at adding acid to base. So we had our super pink basic solutions of sodium hydroxide. So this is NaOH plus our indicator phenolphthalein. So this is pink in a basic environment. We added KHP, which is our acid, until we saw our solution go colorless. This means that we have H2O plus a slight excess of KHP because the indicator, phenolphthalein, is colorless in acidic pHs. So we neutralized plus a little bit extra, which is why we saw that color change. So now in 210, we're going to approximate by saying that the endpoint is more or less what we're going to call the equivalence point. Right? Because we can only witness the endpoint, which we know is some point just beyond the equivalence point, but since we cannot quantify in this class exactly how beyond the equivalence point we are, we're going to say that these are more or less the same. So how does that work with some titration stoichiometry? So most of us have done this already since we had to calculate the molarity of our sodium hydroxide solutions. But let's break this section up into two videos and do an example where we look at how titration can be used to do stoichiometric calculations to figure out things like concentration of different analytes based on the volumes and concentration of titrant added. So that'll come up in part 2, or the second half of this video in part 2 next.